Okay, 8.1 now. So we're on page 614. We're looking at absolute value functions. Taking what we just did with absolute values in 2.1 and applying it now into functions, so equations. Determine each absolute value. Well, absolute value of 3, it's the positive distance from 0, 3. Absolute value negative 4, positive 4. 0 is 0 away, and negative 5 is 0.5 away. What's the absolute value when we plug in a 2 for the x? So in this one we get absolute value of 2 plus 3, which is the absolute value of 5, which is equal to 5. And then absolute value of 2 minus 3, which gives us the absolute value of negative 1, which is 1. And then same thing, absolute value negative 2 times 2 plus 4 equals absolute value of negative 4 plus 4, which is the absolute value of 0, which is 0. And absolute value of 3 times 2 minus 7, which gives us 6 minus 7, absolute value negative 1 equals 1. For this next part, it's a really good idea to try it yourself, to try to figure out and learn this information a little bit on your own, and then see how we apply it further. But you always will learn more if you discover it for yourself. Table of values here. If the x is these ones across the top, what's the y value? Y equals x. Well, just plugging it in, it's going to be negative 3, negative 2, negative 1, 0, 1, 2, 3. But if we look at the absolute value now, and we plug that in, the absolute value of negative 3 is positive 3. Absolute value of negative 2, positive 2. Positive 1, 0, 1, 2, 3. Let's graph the two of them. So graphing the first one, plot all of your points. We've got negative 1, 2, 3, negative 3 and negative 3, negative 2 and 2. Connecting our dots, extending our line. There's your y equals x. And we should always have some numbers on it. So 2, 4, 2, 4, negative 2, negative 4, negative 2, negative 4. So when you are graphing, please make sure you put scale on the axes, put your graph down, label your graph with what equation goes with it. The next one, starting to plot these ones, we've got negative 3 comma 3. Negative 3 comma 3. Negative 2 comma 2, negative 1 comma 1, 0, 0, 1, 2, 3. So now if we graph this one, we have a V shape. Really what's happened here is the negative part of the graph of the original got flipped or reflected about the x-axis. So we reflect that part up and we get the absolute value function. Y equals the absolute value of x. Looking at the domain and range for these. For both of the graphs, the domain is x is the set of real numbers. But if we look at the range now, for the original, the range was all of the real numbers. It goes on forever in either direction. But the range of the second one, so let's look at the range, is y, where y is an element of the reals. So here's your first y equals x. Your range on the absolute value, though, is all above 0, where y is greater than or equal to 0, and y is an element of reals. So the range got changed here. The domain stayed the same as all the real numbers. Okay, so to graph a function now, we create a table of values. And then we would start filling it in. The x-intercept. X-intercept is when y equals 0. Y-intercept is when x equals 0. So we pick some points, some x values, and we start plotting them. And we see what does the graph look like. And as you plot it, you see in your book there, it's already there for you, that we get, again, that V shape. The absolute value functions have a V shape to them because it reflects, it bounces the negative portion of the line up into the positives. So an absolute value function is the absolute value of f of x. And now here's the important part. The critical point is the x-intercept. Notice where the x-intercept was. X-intercept was 4. So we looked at to the left and to the right of 4. And that's where it changes. When it hits the x-axis is where it will bounce back up off the axis. Instead of going like if we said y equals negative x plus 4, it would have continued going on as a straight line. It bounces at the x-intercept. We call that a critical point, because that's where it's going to change directions, at the x-intercept. All right, so if we're asked to sketch the graph of y equals the absolute value of 3x plus 6. First thing we want to do is always, let's just look at what if there was no absolute value. Let's first of all identify the intercepts on 3x plus 6 on the line, and then we'll bounce it. So from here, the intercepts are going to be x-intercept is when y equals 0. So plug in 0 equals 3x plus 6. Subtract over. Negative 6 equals 3x. So x is equal to negative 6 over 3, which is negative 2. There's our x-intercept. We know that it's going to bounce off of that spot. Let's look at what the y-intercept of the original is. So just to have a quick little visual, we know that here is where it's going to be bouncing, creating the V. Let's look at the y-intercept of that graph. That's when x equals 0. So plug that in. Y equals 3 times 0 plus 6. So y equals 6. So we have now here. This is what the line would have looked like. But we know that it's going to bounce off of that spot and mirror. It will mirror for the other side. So we know that if it's negative 2 here, to 6 there, 2 away to the right, it's going 6 up. So that means 2 away to the left, it's going to go 6 up as well. So this point is going to be at negative 4 and 6. It's symmetrical on either side. This one was 0 and 6 at that point. Domain. Okay, so the intercepts are going to be the same for both the two graphs. So x-intercept is one at negative 2, y-intercept at 6. The domain now. You can plug in any x value. There's no restriction on the x value that you can put in there. So we're going to have x is an element of the reals. But now the range of this function, we know that it's going to bounce up and off of the x-axis. So your range, let's put domain, let's do the whole set builder. And then your range is going to be where y is greater than or equal to 0. And y is an element of the reals. Okay, so that next question there. In the example 1 we did, instead of using the worked example of the absolute value of 2x minus 6, let's look at 3x plus 6. And what's the relationship between the two parts of the line, the two portions? We had this one portion and this second portion. So the left side and the right side of where it bounces off. If we look at the relationship, they're symmetrical on either side, but they have opposite slopes. This one had a slope of positive 3. This side here has a slope of negative 3. So the slopes are the same. There's a reflection. It's just an opposite slope. And you can see a similar strategy can be used if we're using quadratic function. We're going to do exactly the same thing. Pretend that we don't have the absolute value to start with. Let's see what does the graph of x squared plus 2x minus 3 look like, plotting all the points. And then we're going to do the absolute value of any of those answers. And if you notice, these are the ones that were negative. So those are the ones that are going to change. So when we graph those, again, it just means that whatever is going to be in the negative section, this yellow section here, gets reflected up to the positives. So that's what the absolute value of a quadratic looks like. It starts off like a parabola, but instead of going into the negatives, it bounces up and it does the opposite direction of the parabola. Or like having the negative a value in front. And then it bounces back up to the positive. I know you've all been wanting to know, how do I use my calculator to do this? I don't want to use a table of values all the time. Yeah, you're right. We don't want to use a table of values all the time. So you have an absolute value feature on your calculator. Again, let's graph this one, see what it looks like. And I want you to actually go through and graph it yourself so you can make sure that you can get a shape that looks like this. We're making sure that we are in a window that we'll be able to see this. You might have to adjust your window, but if you use just the standard window, you'll be able to see it. Okay, so go to your Y1, so hit your Y1 button, and then we're going to enter in your absolute value. Under the math, move over to one side, that's an arrow, move arrow over, hit enter. That gives you that. Secondary thing, the way that actually is a little bit faster to find the absolute value, so you don't have to remember where is everything in my calculator. Everything's in your catalog. Second, 0. On the 0 key, you see the word catalog. So if you hit your second button and your 0, everything's in there. All the functions of this calculator. If you can't remember where something is, go to the catalog. And if you look, it's the first one right on the list. So you can just go second 0, enter. It's a little bit faster, whichever way you want to do it. Then put in the rest of your things. So you're saying the absolute value of this. It's a good idea to close your brackets at the end. So it should look like under y1 equals abs bracket x squared plus 2x minus 3 bracket. Graph that, and you will see the absolute value where it bumps it, reflects it back and up into the positives. the windows that they're using here is, let's talk about the x. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They're using an x minimum, or sorry, x min of -10. Then the x max is +10. The x scale is 1. You're going every tick mark is 1. Y min is equal to -3. 1, 2, 3. And y max equals +10. And y scale equals 1. X-res we don't even ever touch. That's the window that they've used if you want to make it look exactly like what you see there. Okay, so for each of these functions, we're going to sketch the graph. Then we're going to determine that stuff. But we want to sketch it. In order to sketch these, we have to remember what we did with the quadratic chapter. It's still going to apply here. We have to be able to graph a quadratic to be able to graph a question of this type. So let's start by, step 1, sketch this as a graph first. Sketch y equals -2 bracket x plus 2 squared plus 2. If we look at what we have, it's opening down. Negative in front, it's opening down. And then we look at our vertex. The vertex is -2, +2. X-intercepts. Those are always a good thing to know because that's where it's going to bounce off. And also asks us to find them. So we might as well find it right now. So we're going to sketch this one. Let's get our x-intercepts first, because that helps out with the drawing. That's when y equals 0. So plug it in. 0 equals -2 x plus 2 squared plus 2. Subtract the 2 over. -2 equals -2 x plus 2 squared. Divide by the -2. Square root both sides, but don't forget when you use square root, it's plus or minus. So plus or minus 1 equals x plus 2, and subtract that 2 over. So we get x, the x-intercepts are -2 plus or minus 1. Get the actual answers now, which is x equals -2 plus 1, and x equals -2 minus 1. -2 plus 1 is -1, and -3. Let's see what we come up with. Doing a quick sketch of that now. Your vertex was -2 and 2. 1, 2, -2 and 2, 1, 2. Your intercepts are at -1 and -3. Let's find our y-intercept because I want to know where to put that point. Y-intercept is when x equals 0. So just plug in x of 0. Y equals -2 times 0 plus 2 squared plus 2. -2 times 2 squared plus 2. -2 times 4 plus 2. -8 plus 2. Which equals -6. And when I put this here, I say, oh boy, look at this. -6 is down here. I made a mistake. That's the way that you can quickly and easily catch a mistake. It's saying, if I'm drawing this parabola, I know that it would have to have been -2 and +2. There we go. Now I've got the right shape. So from -1, if I go 1 over, it went down 6. So it's symmetrical. Going on the other side, go 1 over, go down 6. That's what it's going to look like. That's the parabola, but I've got to take this portion or this portion and flip one of the two portions. I have to look at which part am I going to flip. Am I flipping this part down or am I flipping this part up? I want it to be positive. It's going to take and make everything positive when we do the absolute value. So it's going to flip these two sections. The negative sections are going to get flipped up. But it's going to be in the same curve as it was going down. There's your graph now. So, let's answer all the questions. The intercepts. X-intercepts are at -1 and -3. They're the same. Y-intercept though. Y-intercept of the parabola was -6. But when I take the absolute value, it's going to be a +6. And then, what's my domain? Domain is all of the real numbers. Range. Y such that y is greater than or equal to 0 and belongs to the set of the real numbers. All right, so let's do the next one. You can always check by plugging it into your calculator, plug the original, plug it into your calculator, see if what you've thought through makes sense, if you've got the right idea. Okay, so let's go through the same thing here. First of all, we're going to start by figuring out where this graph is going to be, the parabola here. Negative, so it's opening down. Vertex is at 0, -1. Let's do a quick little sketch here so we can get started. Figure out where things are. 0 and -1. We know it's opening down. I can see what's going to happen with the intercepts right now. If the vertex is below the axes and it's opening down, we have no x-intercepts. The y-intercept I can read right now because I just plotted it. -1. I don't have to go through and try to find it. There's your parabola. But now we need to do the absolute value, which means take anything that's negative and reflect it to be positive. That whole graph is negative. So the whole graph is going to get reflected up. This point here, which was -1, is going to be absolute valued to +1. Instead of opening down, it's now going to be opening up. Same shape, symmetrical to what was on the other side. But now we can answer. So the intercepts that I have, so this here was for the parabola. Now if we look at the absolute value part, there's still no x-intercepts. It does not cross the axes. The y-intercept now is at a +1. Domain. Domain is always for these, the real numbers. Really only changes when we deal with word problems. And the range. The range is above 0, but it's actually greater than or equal to the vertex at this point. So y is greater than or equal to +1. And instead it's reals. Just to get a nice visual, better than my chicken scratch, here's your
Mr. Villamil, call the office, please. Mr. Villamil.
there's your information with a nice graph so you can see what they look like. Okay, so there is going to be a time when the quadratic function and the absolute value of the function are going to be the same. We just saw in that last example that it reflected all the way up and over the axes. When would they be exactly the same? Well, what if I had my vertex above the axes and it opened up? I have no negative portion of the graph. If the vertex is at or above the x-axis and it opens up, the graphs are always going to be the same. So you'll want to put that into your own words there. Piecewise notation. This, for some students, is a little bit of a tricky thing to get started with. Piecewise notation is, let's take the two different portions of the graph, the part that was positive already and the part that got reflected, and we're going to break it up into two different equations. So, for example, this isn't in your book. I can go through the example. The BC Wildlife Park offers discounted admission rates for groups of 10 or more. The rate for one adult depends on the size of the group. Okay, 1 to 9, 10. Okay. Let R represent the rate for one adult in dollars and N number of people. Piecewise notation. Break it up into the three different parts. If we have between 1 to 9, meaning numbers is between 1 to 9, then the value is going to be 10. That's the rate. If, however, we have 10 to 99, inclusive of those numbers, we have a value of 8. If we have 100 or more, n greater than or equal to 100, it's going to now be 7. We're going to do the exact same thing with absolute values. We're going to break it up into its portions. Okay, so the absolute value of a number is often defined in piecewise notation, just like this. The absolute value of x, well, we could have had a positive x or we could have had a negative x in there. And what we say now is that the value of it is positive above the x-axis when x is greater than or equal to 0. This portion here. So when x is greater than or equal to 0, really what we're saying is y equals x here. The value is the same as the x. But if I have less than 0, that means this portion over here, it got reflected up to be equal to y equals negative x. The two different portions of the graph. Positive portion, which includes 0. Notice this right here. It's greater than or equal to 0. And then the negative portion gets the less than 0, not equal to. To write an absolute value function in piecewise notation, start by identifying when the expression is positive, 0, and negative. Where does it bounce off the axes is really what we're asking. The x-intercept. All right, so then we've got, first find the x-intercept, that's your step number 1, right there. Then identify the places where it's positive. It's already originally of the line going to be above the x-axis to the right. Okay. So we're going to talk about this section now. The original line would have gone going up positive, so that's when x is greater than the negative 2, or equal to the negative 2. That gave us the positive. So we're going to keep it as the positive.
Sorry for the...
That's the positive part. Then you've got your when x is less than 0, coming up the other side. That was the negative expression for it. We've got the negative. We needed to flip it up from its original. So now we go into a piecewise function. We're saying y is equal to positive x plus 2, the blue side, when x is greater than or equal to the bouncing off point, the x-intercept, when it's greater than or equal to negative 2. Y is equal to the negative version of that when we have it less than negative 2. Okay, so before starting this next third example, I highly recommend that you pause, that you look at their example for A and B, and then pick back up to see how I'm going through. But have a little bit of an idea of where we're going and what we're doing. Okay, so for the first one, I'm going to call the two different parts case 1, the positive case, and case 2, the negative case, because I'll be using that later on. So case 1 is going to be positive case. The positive case happens when what's inside 2x minus 1 is greater than or equal to 0. We always take the positive as the greater than the equal to 0. And now just solve for x. 2x greater than or equal to 1, x greater than or equal to 1/2. So we're saying here is that y equals, opening up the big brace, y is going to be the positive case, 2x minus 1, when, or if, x is greater than or equal to 1/2. Okay, so the case 1 is going to be y equals 2x minus 1 when this happens. X is greater than or equal to 1/2. Case 2, which is the negative case. This one occurs. What we'll have is y equals the negative bracket 2x minus 1, the negative part of the graph, or y equals negative 2x plus 1. This happens when what's inside there, 2x minus 1, is less than 0. So then solve for x here. 2x is less than 1, x is less than 1/2. So it'll happen. This equation will be when this happens. So in other words, negative 2x plus 1 will be the equation if x is less than 1/2. Okay, next one. Good idea to try it yourself. So case 1 is the positive case. Positive. Or y equals negative x squared minus 3x. So for this first case, the positive case, it's easiest to look at where is the related parabola already above the x-axis. So we look at it and say, oh, it's opening down. And where's the x-intercepts of those? So let's find x-intercepts. The x-intercepts for this would be when negative x squared minus 3x equals 0, when the y equals 0. Let's factor. We get, let's pull out a negative x equals x plus 3 is 0. So either x equals 0 or negative 3. So at 0 and negative 3 are where the x-intercepts are, and it's opening down. So that means if it's opening down, it had to have been up in between those two values. Or in other words, we will have y equals, open brace, the positive, whatever exactly as it is, negative x squared minus 3x. That's going to occur if the x is between these two values. Negative 3 less than or equal to x, less than or equal to 0. And now we are going to look at the opposite side, which would be y equals the case 2, the negative case, negative bracket, negative x squared minus 3x. Distribute that in, we're talking about x squared plus 3x. That's going to happen, x squared plus 3x, if, well, from the original parabola, it would have been going down in either directions. So that means that we had to have flipped those parts up. So it would have been flipped up to the opposite, less than negative 3, and flipped to the opposite, greater than 3, or sorry, greater than 0. So if x is less than negative 3 or x is greater than 0. The equal to sign goes with the first case, leaving it as such. Okay. The other signs go with the second case. Okay, so in order to use your calculator to graph a piecewise function, go into the y equals, and we're going to plug in each of the two different sections. So section 1 and section 2. So bracket negative 4x plus 4, end your bracket. Now open your bracket. We want to find your inequality signs. So x, it's in second math. So second math gives you your test features. We're looking for the less than or equal to, so number 6, the 1. End your bracket. Enter. Put in the other side now. 4x minus 4. 4x minus 4. Oops, got the bracket. Bracket, and then put in your x second now. And down we want number 3. And 1. And when we graph this one now, you'll see it'll graph the two different portions, which would be the same as saying the absolute value of negative 4x plus 4. And just so we can see it draw, I'm going to put it as a thick line. And you can see that it drew right over top of the other one. So piecewise is a little bit tricky. I will go over it again. But please do your discuss the questions 1 to 3 there.